NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams. And all these little dots are stars?
All these little dots are galaxies, some of which are bigger than our own.
Breaking news. We may have just found potential evidence of intelligent life beyond Earth.
This is a huge discovery, and we think that it's a huge discovery. And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Well, JWST is so phenomenal that if you spend enough time, you could probably find any galaxy that ever formed in the universe. It's really that powerful.
Pluto, a far-off and confounding body, was once viewed as a solitary and veritable planet, an individual member of our planetary family. However, late and unsettling declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a surprising discovery. They suggested that this cold world is on a potential impact course with Neptune. But how could this happen, and what might be the consequences of such an epic event? Are we witnessing an intriguing cosmic anomaly, or is there more to this impending celestial occurrence? Join us as we explore the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was demoted to a lesser status, remains a subject of interest and study in the astronomical community. According to precise calculations by leading experts, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are raising the alarm about a potentially catastrophic collision between these two celestial bodies, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's orbit around the Sun is unique compared to any other planet in our nearby planetary system. It takes an astonishing 248 years to complete a single orbit, which means that since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is characterized by its highly eccentric shape, vastly different from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination of 17 degrees to the ecliptic plane. The path Pluto follows is far more erratic compared to other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. Perhaps one of the most captivating aspects of Pluto's orbit is its interaction with Neptune's orbit. For at least 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, contrary to what we would expect based on their positions in the planetary system. This raises an obvious question. Why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The analysis of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to explain its peculiar trajectory. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood apart with its dangerous inclination and unpredictable shape. The mystery surrounding Pluto's orbit can be explained by the three-body problem in celestial mechanics. This problem involves understanding how three objects in space, such as Pluto, Neptune, and the Sun, move and interact with one another through their gravitational forces. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem illustrates how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complex way. Terms like asymptotic libration, scope libration, and the VZK wobbling are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is a type of libration. In the case of Pluto and Neptune, this means that whenever Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is essential in preventing their orbits from affecting each other. Degree libration, on the other hand, refers to the vertical motion of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or another giant planet, it is positioned far above their orbital plane, adding an extra layer of protection from potential collisions. Another critical factor in this situation is the VZK wobbling, named after three scientists, Valv and Ku, who studied how objects move in space. This concept explains how three celestial objects like Pluto, Neptune, and the Sun interact gravitationally, affecting their movements. In Pluto's case, the VZK wobbling helps us understand why its path near the Sun is so unusual. Despite the apparent randomness, this effect helps keep Pluto's orbit stable for incredibly long periods. The VZK wobbling shows that even though space may seem chaotic and unpredictable, certain patterns and forces help maintain order. These dynamics help regulate Pluto's orbit, ensuring it doesn't collide with Neptune or veer off course. This three-body problem influences how we understand these orbits, particularly how celestial objects interact gravitationally. Focusing on this helps us study Pluto, our neighboring planetary system, and distant stars and planets. Numerical simulations in the late 1980s revealed that, despite these predicted properties, Pluto's orbit still exhibits small deviations in initial conditions, leading to significant differences over long periods. However, these odd characteristics of Pluto's orbit have been found to maintain consistency over extremely long timescales. Later computer models have helped us understand how the giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only factor. Jupiter's gravity also plays a significant role in stabilizing Pluto's orbit, with Saturn contributing as well. These experiments show that Jupiter's gravity alone is strong enough to ensure Pluto remains on a steady course for a very long time, possibly even billions of years. Perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto can continue orbiting safely in space without running into trouble. These peculiarities are crucial in the larger context of the universe for maintaining the stability and consistency of celestial bodies. Without these factors, our nearby planetary system as we know it would be a place of far greater chaos and instability. Bodies like Pluto could indeed collide with others or be ejected from their stable orbits, triggering a chain reaction affecting other celestial bodies. For Pluto, especially with discussions about it potentially colliding with Neptune in the future, understanding its orbit is essential. This gives us a clearer picture of the dynamic nature of neighboring planetary systems. The case of Pluto and Neptune demonstrates the intricate ballet of gravitational forces that governs our solar system. Despite its apparent unpredictability, Pluto's orbit is remarkably stable over vast time scales. This stability arises from the delicate interplay of gravitational resonances, inclinations, and orbital eccentricities. Without such intricate dynamics, the solar system as we know it could be far more chaotic. Astrophysicists emphasize that the current stability does not entirely rule out potential disruptions in the distant future. Factors like gravitational interactions with passing stars, rogue planets, or even the movement of the Sun and its galactic environment could introduce perturbations over billions of years. Such events might alter the delicate equilibrium, potentially leading to collisions or ejections. The possibility of a Pluto-Neptune collision, while captivating, remains extremely unlikely due to the mechanisms that have preserved their orbits for so long. Yet, studying such scenarios provides invaluable insights into celestial mechanics and helps refine our models of orbital dynamics. Beyond the academic fascination, understanding these phenomena is critical for broader astrophysical research. It informs how exoplanetary systems evolve and how chaotic factors may shape planetary habitability elsewhere in the universe. The study of Pluto's complex orbit is not just about one dwarf planet, but about unraveling the cosmic clockwork that keeps our universe in motion. As researchers continue to explore Pluto and its interactions, the story of this distant icy world reminds us of the intricate and often surprising nature of our solar system. Pluto's journey, from its reclassification as a dwarf planet to the possibility of colliding with Neptune, underscores the ever-evolving narrative of astronomy, where each discovery opens new doors to understanding the cosmos. In conclusion, while the notion of a Pluto-Neptune collision sparks the imagination, it remains a testament to the precision and complexity of orbital mechanics that such events are avoided. For now, Pluto continues its lonely trek through the outer reaches of the solar system, a small yet significant piece of a much larger cosmic puzzle. Pluto shows how, even in the most evidently unsound circles, an equilibrium can be accomplished through the mind-boggling collaboration of gravitational forces and orbital mechanics. It additionally highlights the significance of consistent observation and investigation of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital resonance, which implies the delicate dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in Pluto's case. This means that even slight changes in the dwarf planet's position or speed can significantly alter its long-term orbit. Utilizing virtual simulations has been crucial for researchers to comprehend how Pluto moves in space. These models use complex mathematics to simulate how Pluto, along with other space objects like Neptune, exerts gravitational forces on one another. By altering small details in the simulations, astronomers can observe how even minor changes can have a massive impact on where Pluto ends up. In the late 1980s, these simulations revealed something very intriguing about Pluto's orbit. Despite having mechanisms like asymptotic libration and expansion libration to stabilize it, its orbit can still be remarkably unpredictable. If you begin with even a slight difference in Pluto's position or speed, its path could end up looking completely different over many years. Nevertheless, Pluto's orbit remains stable for billions of years. This suggests that Pluto's journey around the Sun has a certain order to it, even though it initially appears chaotic. Especially with irregular orbits like Pluto's, this presents enormous challenges. The inherent nature of these systems suggests that long-term predictions are often filled with uncertainties. While numerical simulations are an essential tool for understanding and predicting the future behavior of celestial bodies, they also highlight the limitations of our forecasts. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight mistake or deviation can drastically change the results, making precise predictions an overwhelming challenge. Furthermore, the turbulent nature of large orbits like Pluto's serves as a reminder of the ever-changing and dynamic nature of the universe. While we've made tremendous strides in understanding space, Pluto's case reminds us that our understanding of the universe is still limited. Understanding the gravitational effects of the giant planets on Pluto's orbit offers valuable insights into the broader dynamics of the solar system. It demonstrates that the presence and position of each planet can have sweeping effects on the stability and trajectory of other bodies within the system. So, why are prominent astrophysicists suddenly raising concerns about a potential collision between Pluto and Neptune? Despite these complex forces working to prevent such an event, Neil deGrasse Tyson, a renowned astrophysicist, offers a book-length perspective on the mysteries of our solar system, particularly the fascinating example of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public's interest in the unexplored corners of space. His stance on Pluto's reclassification is framed within the ever-expanding knowledge of our solar system. He views the reclassification not as a demotion but as a necessary adjustment to our growing understanding of the many bodies surrounding our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He recognizes the complexity of Pluto's orbit and its interactions with Neptune from a perspective that acknowledges the unpredictability of space. He suggests that while Pluto's orbit is stable for now, it could undergo significant changes in the future. This possibility serves as a reminder of how much we still have to learn about the forces shaping our solar system. In essence, Pluto's orbit is a fascinating case study in the intricate interplay of gravitational forces within our solar system. While its orbit is stable for now, the mysterious dynamics between Pluto, Neptune, and other planets suggest that even the most seemingly stable orbits could change over time. As astrophysicists like Neil deGrasse Tyson continue to study the mysteries of the universe, they help us better understand the delicate balance that governs the movements of celestial bodies. The potential for a Pluto-Neptune collision is not necessarily imminent, but it serves as a reminder of the ever-evolving and confounding nature of the universe. Despite the established theories surrounding Pluto's orbit, it is crucial to consider the broader implications of these dynamics for our understanding of the solar system and the universe at large. Pluto's journey is one of fascination and serves as a reminder that the universe is filled with mysteries and complexities waiting to be explored. The concept of orbital resonance, particularly between Pluto and Neptune, is a central piece of the puzzle. This resonance, where the ratio of Pluto's and Neptune's orbits is 2:3, is a fundamental aspect of celestial mechanics. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance ensures that, despite their orbits crossing, the 2 planets never collide. This is a result of the gravitational interactions that stabilize their paths, working together to prevent any catastrophic impacts. The importance of resonance in maintaining stability cannot be overstated. It provides a fascinating example of how systems in space, even those that initially appear chaotic, can self-regulate through subtle gravitational forces. Understanding this resonance also explains why Pluto, despite its irregular orbit, has remained stable for billions of years. This dynamic is a key part of the larger structure of the solar system. The effects of planets like Jupiter, Saturn, and even Uranus are vital in maintaining stability in the orbits of smaller bodies like Pluto. Jupiter, with its massive gravitational force, acts as a kind of guardian for the solar system, influencing the paths of various asteroids and dwarf planets, including Pluto. In fact, some experts speculate that Jupiter's gravity could have prevented Pluto from being ejected from the solar system entirely. Without Jupiter's protective influence, Pluto's orbit might have been disrupted even further, potentially sending it out of the Sun's gravitational reach.